Time we talked about, what did we talk about? I'm all out of, oh yes, pHs of salts, pH of salts. We're going to continue that just with one problem today, and then we're going to move on to looking at acid structure and predicting strength. And then moving on to chapter 17, looking at common ions and then buffers. So, this seems loud. Okay. There's a couple of things that we're going to look at today that are within this problem that aren't sort of super obvious. The first one is that, what is this pyridinium bromide? Okay. So this is a salt. It is a salt that makes a basic solution. Okay. So when we put this salt in solution, sorry, I don't have my normal pencil here, so this might not be great today. You have C5, I might have to go upstairs, H5, NH, yeah, I'm going to have to run upstairs. It's not going to work. All right, give me 2 minutes, I'll be back. Well, during those 2 minutes, why don't you all try to work out that problem? This is the pH of a salt. Expect a basic solution. Remember, we're given K, or no, sorry, this is going to form an acidic solution. Sorry, I'm all out of whack. You're given a Kb, you're going to need a Ka, that kind of thing. So watch that. Go ahead and give that a try, and I'll be back shortly. Okay, so my apologies. Pyridinium bromide. We put that into solution, and it completely dissociates into C5H5 NH plus and Br minus. Okay. This is a type of base that I want you to be aware of. Sorry, this is an acid. I'm losing it today. I've already done like those lectures upstairs, so now I'm just sort of exhausted. So we're going to put this in solution. And it's going to react with water, to form H3O plus and C5H5N. Okay, that's the conjugate base. Okay. So this should look similar. What I wanted you to see, this compound should look similar to what we see for ammonium ion. All right. The NH4 plus of ammonium and the NH plus for this compound. The H plus hopefully will signify to you that that could make an acidic solution. That's going to donate its proton to water to form H3O plus. Okay. There are, sidebar before we finish this problem, there are bases that look similar to this that I want you to be aware of, and they're called amides. Okay. They look similar to this, the conjugate base of this problem. Okay. They will often have the formula X, something like CH3, for instance, and then NH. Okay. So XNH. That's methylamide. You might see ethylamide, C2H5NH. Okay. These are bases. So I want you to be familiar with what these look like and be able to sort of recognize them. I want to make sure I've done something correctly here. Wasn't methylamide and Breaking Bad? Was that what they got from the train? Do we know? Do we need to go back and watch the whole thing? Yeah, okay, yeah, that's correct. Okay. So this is a type of base, these amides. Of course, you know the other types of bases, things that have OH in them, like NaOH, KOH. And there's one more type of base, which are the conjugate bases of weak acids. WA, weak acid. Okay. Just sort of categorizing some bases. These are ones that I want you to be familiar with. Okay, so pH of a solution when we have 0.1 moles of pyridinium bromide dissolved in 1,000 milliliters of water. So we have 0.1 moles per liter of C5H5NH+. If we want to abbreviate that, we can do BH+, and then B for the conjugate base. Okay. So again, this is an ice table, all right? So we do a salt, we put a salt in water. We know how it's going to dissociate because we all remember the solubility rules. And then we can set up an ice table. So we have 0.1 mole per liter of our BH+, 0 moles per liter on the product side. We have minus X on the reactant side, plus X on the product side. Okay, everyone okay with the ice table? Okay. I always tell you with these salt problems that you're most likely going to be given the Ka when you need the Kb or the Kb when you need the Ka. That's also true here. So we have the acid form on the reactant side, the H plus one, right? So now we need to use a Ka to solve for X using the equilibrium constant. So we need Ka, we were given Kb. So Ka is going to be equal to 1 times 10 to the minus 14 divided by 1.7 times 10 to the minus 9. And we'll get 5.9 times 10 to the minus 6. Okay. We can determine if X is small when we set up our full equilibrium constant expression. So this is equal to X squared concentration of products divided by the concentration of reactant. We can determine if this X is small by looking at the initial concentration, 0.1, divided by the Kb. And it is small, so I'm not going to do the math. It's greater than 1,000, this value, so we can ignore X in the denominator. Then solving for X, we're going to get X is equal to 7.67 times 10 to the minus 4, and that is equal to H3O plus from our ICE table. And so we can take minus the log of that value to get the pH. Equals 3.12. I know I went very quickly through that. Salts problem. Understand the association of the salt. Then figure out which of those components of the anion or the cation is going to affect the pH of the solution. Consider that anion or cation's equilibrium using ICE table to calculate X and figure out if the X is H plus or H minus. Yes.
Should there be 3 sig figs after the decimal?
Should there be 3? Yes, probably. If I'm correct in my X values, sig figs. I get really sloppy on sig figs. I apologize. Other questions about? Yes.
So the question is that for chlorine, so Pb is that number. So would that be the number to put chlorine in water, or?
So this is what you're referring to, the Kb?
Yeah.
Yeah, so pyridine is essentially, it was this. Yeah, so we didn't end up using the Kb directly, we used the Ka. And because the pyridine and the pyridinium are conjugate acid-base pairs, when we have the Kb for pyridine, we can use the Ka in this case for pyridinium because it's on the reactant side. Yeah.
I just want to clarify, for checking the assumption,
Yeah.
throw 0.1 per kg and then use Ka.
Oh, you're right, I did. It should be Ka.
Okay, thank you.
Whatever K you're using, the correct K. Yep, thank you. Other things? Yes.
So would use Ka if the reactant is an acid?
Yes, exactly. Use Ka if our reactant is an acid, use Kb if it's a base. So then the tricky part is identifying if it's an acid or a base. Yeah.
When you dissociated the C5, H5, and HBr solid,
Yeah.
and it became Br minus and then the other cation, how did you know which one to pick?
You mean instead of why didn't I pick
Br
Br minus?
Yeah.
Because I'm thinking about what the equilibrium with water would look like for Br minus. So So I didn't show this step, you're correct here. Br minus plus H2O, its equilibrium would look like forming HBr and OH minus. But we know that HBr is a strong acid. And so we know then that this reaction won't occur, which means Br minus, because it's a strong acid, is completely dissociated. Yep. And so Br minus does not affect the pH of the solution. So any of the anions of the strong acids don't affect the pH. Any of the cations of the strong bases don't affect the pH, and those are nice and easy to recognize, the group 1 and 2 elements. Okay, I'm going to keep moving. So if you didn't see on Carmen, I uploaded a new file called N16. It's under today's lecture slides. There's just 2 new things that I've added. They show up when we're looking at acid strength, so you might want to grab those if you haven't already. But there's a summary slide here, and for time I'm not going to go through all of this, that looks at how to calculate pH or pOH for several different options of substance. Strong acid, strong base, weak acid, weak base, and then conjugates of weak acids. So this comes in with salts, this last row. And so, it kind of walks through, and as we go down this list, things get more and more complicated, okay? So take a look at that if you're struggling. It might help you get started. Okay. So then, let's talk a little bit about acid strength and structure. I added these slides because there's a very good chance you will see these types of things on your exam. So, acid strength and structure. There are 3 factors that affect acid strength that are related to its structure. The first one, and again, we're considering an acid. It could be a strong acid, it could be a weak acid, but the acid is going to be represented by H for the proton and A for whatever is bonded to it. Okay? So the bond polarity is the first thing, and you may recall writing bond polarity sort of like this, where we have a partial positive charge, and in this case it's going to be on the hydrogen, and a partial negative charge. In this case it's going to be on the other stuff bound to the acid. Okay? Maybe you didn't, but that's what that sort of means. Okay? So what we see is that as bond polarity increases, so the polarity between the hydrogen and whatever it's bonded to, as that increases, the acid strength increases. Okay? And when we're talking about acid strength increasing, that means we have a larger Ka. And in reality, there's some amount of, well, no, I'm not going to go there. Never mind. Okay. Then the reason for this is that when this, what it means when this bond polarity is larger is that the A portion is more electronegative. So it's able to withdraw electron density away from that proton, which makes the proton easier to leave. Okay. It also does affect what we see here in number 3, which is the conjugate base stability. Okay. The next factor is the strength of the bond between the proton and what it's bound to. If something has a weaker bond, a weaker H to A bond, it's a stronger acid. And then when it comes to, we're going to take a look at these examples in a bit more detail, but when it comes to conjugate base stability, if the A minus, the conjugate base, is more stable, then we have a stronger acid. And often it can be difficult to predict what a stable conjugate base is. So I wouldn't worry too much about that. Let's focus more on the first two, bond polarity and bond strength. And we can have, well, of course, all bonds have a polarity and all of them have a strength. And so we're going to call these rules or patterns into effect depending here. Okay. So this kind of asks you to recall periodic trends. If we're looking at binary hydrides, so let's look at group 7A specifically. HF, HCl, HBr. Right? We know that HF is a weak acid, okay? And HCl and HBr are strong acids. What we see is that as we go down the periodic table, the acid strength increases. Now, we have a different A, in quotes here, bound to each proton. So H to F, H to Cl, H to Br, right? So the thing that's really changing here, electronegativity is changing, but the thing that affects these, this trend most is actually the bond strength. And that's not something you would necessarily know just by looking whether electronegativity or bond strength is greater, but experimentally, it becomes a bit more obvious. So with HF, the bond enthalpy, which is a measure of the bond strength, so how much energy is required to break the bond, is 567 kilojoules per mole. For HCl, that decreases to 431, and for HBr, it decreases even further to 366 kilojoules per mole. So the bond strength decreases as we go down this list of group 7A hydrides. When the bond strength is stronger, the proton is less likely to leave. The Ka is smaller. Does that make sense? Okay. But what if we have the same atom bonded to each proton? So in this example, these examples, I don't like how this is written exactly. It says Y-OH, which makes me think, or might make you think that OH is going to be what's leaving because it kind of makes it look like a base, right? These are all acids. Okay, these are all acids. So really what we need to be thinking about is Y bonded to oxygen, bonded to hydrogen, and the bond that's going to be breaking is this hydrogen-oxygen bond. So we're still going to form proton, where H plus is still going to leave. Okay, just wanted to clarify that. In this case, because oxygen and hydrogen are the ones that are always bound, the bond strength is always the same there, essentially, very close at least. And so electronegativity becomes more powerful in how it affects acidity. Okay? And so if we look here, hypochlorous acid, ClOH, hypobromous, hypoiodous, the Ka's decrease now as we go down the group. HCl, OH, or excuse me, ClOH, ClOH, BrOH, IOH. Okay? The Ka's decrease, and that is because the electronegativity decreases. Okay? As the electronegativity decreases, well, let me do that the opposite way. As the electronegativity increases, it pulls electron density away from the oxygen to hydrogen bond, making that bond easier to break. And that conjugate that's formed is more stable. Okay? So in this figure, it says protons are more readily transferred to water. And basically that means that H plus is able to leave the rest of that molecule much more easily. The last set, and these are all in your textbook, so please read this section. are the oxy acids. Okay. So we have hypochlorous, chlorous, chloric, and perchloric, which are the most annoying names to memorize. But as you can see, we've seen HClO4, okay? That's this one. This is a strong acid, okay, and the Ka is listed as very large, basically immeasurable. And I had asked one time, maybe it was last lecture, about HClO3, if we listed that as a strong acid in this textbook or not, because the Ka there is also very large. In any case, the acid strength increases as we increase the number of oxygen atoms around that central atom, so around the chlorine in this case. And again, this has to do with electronegativity. There's more oxygen, more electronegativity around the chlorine that draws electrons this direction away from the hydrogen-oxygen bond, allowing that bond to break more easily. Okay? So 2 factors, bond strength, and that's when we're comparing hydrogen bonded to some other atom, and each of those atoms are different. If the atom that the hydrogen is bonded to is all the same, we most likely need to invoke the purpose, or invoke electronegativity in our reasoning. Questions on any of that? All right. That's the end of that little set of slides. That is